Now that we have what we might call a good fundamental understanding of chemical equilibria, we are in a position to learn how to solve what we might call a number of classic types of problems that students are usually expected to be able to solve in a first-year high school chemistry class. You will probably be very shocked by the statement that I am now about to make. You already know absolutely positively everything you need to know to solve, in principle, any equilibrium problem in the entire world. Because, as we mentioned earlier, the only thing you really need to understand is what an equilibrium constant is, how you write it, and what its numerical value tells you. But don't get too relaxed. In actual practice, equilibrium problems are so diverse and range so widely in their level of difficulty that you could literally spend an entire semester learning how to solve equilibrium problems and still not cover every possible type. So while in principle we have all the background we need to solve any equilibrium problem, in practice things aren't that simple. You need a lot of practice. You need a lot of exposure. You need a lot of experience in order to become good at solving equilibrium problems. So most of the remaining lectures are going to have as their focus these types of problems. But remember, there really aren't different types of problems. There's really only one problem, and it involves only a few basic concepts. But there's probably no topic in a high school chemistry course better than equilibrium at pulling together all the things that we've learned to this point. The first type of equilibrium problem students are asked to solve, I personally think is also the simplest. And that's where you're given the equilibrium concentrations of all the reactants and products, and you're asked to calculate the value of K. Here's an example. Consider the reaction between carbon monoxide and hydrogen to form methanol, CH3OH. Given the equilibrium concentrations you see on the screen, find the numerical value of K. I said that I consider this to probably be about the simplest type of equilibrium problem. I would even go so far as to say that it's hardly an equilibrium problem at all. I mean, it's more like an algebra problem. I mean, it is an equilibrium problem only in the sense that you have to know how to write down the correct expression for K. But if you know how to write the correct expression for K, this really comes down to just plugging the numbers in correctly and then using your calculator correctly. According to our rules, K would equal the concentration of CH3OH divided by the product of the concentration of CO times the concentration of hydrogen squared. So plugging in the numbers, the concentration of CH3OH was 5.05 molar, the concentration of carbon monoxide was 0.65 molar, and the concentration of hydrogen was 0.86 molar, and that has to be squared. This comes out to be a value of about 11, 10.5 if you want to carry an extra digit. Either answer is okay with me. And I'd like to make one comment about this problem and equilibrium problems in general. When solving equilibrium problems, we typically do not attach units of concentration to any of the substances in the equilibrium constant expression, nor do we include any units on the value for K itself for reasons that are beyond the scope of this course. This is kind of in conflict with our normal practice of including units on all numbers. But if you try to include units in equilibrium constants, they will be of no use whatsoever and will only serve to mess up everything, so units are not carried through the solution to the problem. But the proper units should always be attached to your final answer. Okay, let's try another. Given the reaction between sulfur dioxide and oxygen to form sulfur trioxide and the equilibrium concentration shown, find the value of K for this reaction. This problem is basically just like the last problem. The only challenge is to make sure that you write down the equilibrium constant expression correctly, remembering to square the concentrations of both sulfur dioxide and sulfur trioxide. Make sure you line up each of the concentrations given with the correct substance, and then make sure that you evaluate the expression correctly. which means remembering to raise each concentration to the appropriate power and using your calculator correctly. Plugging in the numbers given in the problem, the concentration of sulfur trioxide was 0.3 molar, and that has to be squared. The concentration of sulfur dioxide was 0.044 molar, and that also has to be squared. And the concentration of oxygen was 0.16 molar. If you evaluate this correctly, you will get an answer of about 290, or 2.9 times 10 to the second in scientific notation. Okay, that's the first, and as I said, I think the easiest kind of equilibrium problem. So let's take a look at another type of problem, slightly different, but really very similar to the first two we've worked. Let's go back to the equation we used for our first problem, the reaction of carbon monoxide and hydrogen to form methanol, for which K is equal to 10.5. Given the equilibrium concentrations of carbon monoxide and methanol that you see on the screen, find the equilibrium concentration of hydrogen. When I say this problem is related to the first two problems we've seen, what I mean is that in the first two problems, we were given the equilibrium concentrations of all the substances involved in equilibrium, and then we're asked to calculate K. This problem is just a little bit of a variation on what is basically the same thing. Now, instead of being given all the equilibrium concentrations and asked to find K, we are given K and two of the three equilibrium concentrations, and then asked to find the third. So once again, this really is more of an algebra problem than a real chemistry problem. We said that K would equal 10.5. The equilibrium concentration of methanol was given as 2.33 molar. The equilibrium concentration of carbon monoxide was 1.25 molar, and we were supposed to find the equilibrium concentration of hydrogen, and that concentration is squared in our equilibrium expression. So there's the correct setup. All that's left is the algebra and calculator work. We can solve this quickly or more slowly, depending on how good our algebra is. I'll do this first one rather methodically. First, we'll cross-multiply. So cross-multiplying, we get that 2.33 equals 10.5 times the denominator of the equilibrium constant expression, or 10.5 times 1.25 times the concentration of hydrogen squared. Then, dividing both sides by 10.5 and 1.25, or rearranging the expression however you think of it, we get the concentration of hydrogen squared, and that's very important, is equal to 2.33 divided by 10.5 and divided by 1.25, which equals 0.178. 0.178 is not the answer to the problem. That number does not equal the concentration of hydrogen. It equals the concentration of hydrogen squared. But our task was to find the concentration of hydrogen, and that would be equal to the square root of 0.178. So you need to know how to take the square root of a number on your calculator. Again, if you don't know how to do that, you'll have to consult the manual that came with your calculator, ask your math teacher, or something. Since all calculators are different, there's no way for me to provide specific instructions on how to do this. The square root of 0.178 comes out to be equal to about 0.42. And an important thing to remember is that after you obtain your numerical answer, be sure to put the proper units on the answer. The concentration of hydrogen isn't 0.42. It's 0.42 molar. And here's another slight variation. Solid silver chromate, Ag2CrO4, is in equilibrium with its aqueous ions, silver ion and chromate ion. The equilibrium constant for this reaction is equal to 2.4 times 10 to the minus 12th, a very small value. Given the equilibrium concentration of chromate ion shown on the screen, what is the equilibrium concentration of silver ion? I'd like to make a comment here. You may have noticed that in the original statement of the problem, an AQ was put in parentheses after the symbols for the silver ion and the chromate ion. As we mentioned several lectures ago, This indicates that these ions were in solution in water. But I've eliminated this designation in the presentation of the solution to the problem because it is generally understood that when nothing is written after the symbol for an ion, we assume that it's dissolved in water. This is done just for convenience, so we don't have to keep writing AQ time after time after time. Okay, let's see how this problem works out. The equilibrium constant expression for this reaction would be equal to the concentration of silver ion squared times the concentration of chromate ion. Note that there is no denominator in this expression, or more correctly, the denominator is understood to be 1. If you remember, in lecture 23, we learned that you never include pure solids or pure liquids in an equilibrium constant expression. Since the reactant here is solid silver chromate, it should not appear in the equilibrium constant expression for this reaction. So K just equals the concentration of silver ion squared times the concentration of chromate ion, and this is equal to 2.4 times 10 to the minus 12. The concentration of chromate ion was given in the problem and was equal to 3.8 times 10 to the minus 4th molar. We were supposed to find the concentration of silver ion. So all we really have now is an algebra and calculator problem. The concentration of silver ion squared, it's easy to forget that, is equal to 2.4 times 10 to the minus 12th divided by 3.8 times 10 to the minus 4th, which comes out to be 6.32 times 10 to the minus 9th. So the silver ion concentration would equal the square root of that, or 7.9 times 10 to the minus 5th molar. And remember to attach the proper units to your final answer. So that brings us to another problem. At this point, you may be grinning like the proverbial Cheshire cat, thinking that these equilibrium problems are the easiest thing we've done yet. So let me warn you that the next problem is very, very different. So think carefully as you attempt to solve it. Consider the equilibrium system you see on the screen. 1 mole of H2S was placed in a 1-liter container and allowed to establish equilibrium. At equilibrium, the concentration of S2 was measured and was found to be equal to 0.15 molar. That's what's meant by the phrase, at equilibrium, square brackets S2 equals 0.15 molar. Calculate the value of K. And you notice that it says hints to follow if needed. Why does it say that? It says that because we are taking a quantum leap and going from the previous problem to this problem. If you are brimming with confidence, you might want to tackle this problem. But if you feel you could use a little help, instead of pausing the video at this point, watch these hints. The problem says that 1 mole of H2S was placed in a 1-liter container and allowed to establish equilibrium. What this is telling us is that I took a container, 1 liter in volume, and into this container I placed 1 mole of H2S. Well, I suppose it's fairly obvious that this makes the concentration of H2S 1 molar. So you may be thinking, okay, I get it. I just plug in 1.0 molar into the equilibrium expression for K. No, absolutely not. Au contraire, as I like to say. Here's the most critical point. This is not an equilibrium concentration. This is what I put into the container initially. Now you may recall that we said initial concentrations are indicated by putting a little subscript of 0 below the symbol for the concentration of something. I began with 1 mole per liter of H2S in the container. But when I want to calculate a value for K, I have to use equilibrium concentrations, not initial concentrations. K must be calculated from the concentrations of all reactants and products after you get to equilibrium. So what does this mean? It means that the equilibrium concentration of H2S is not going to be equal to 1 molar. Because if I begin by by only putting H2S in the container, some of the H2S is going to have to decompose and turn into hydrogen and sulfur in order to establish equilibrium. Let me repeat that because it's a very important point. If I put nothing but H2S in the container initially, and that's what the problem says, 1 mole of H2S is placed in a 1 liter container. That system cannot possibly be at equilibrium because there are no products. So the system is going to shift to the right. H2S is going to decompose to form hydrogen and sulfur. Now the problem tells me that when I finally get to equilibrium, the concentration of sulfur is measured and it is found to be 0.15 molar. And they want you to calculate the value of K. Now, if you go back to the original few problems that we worked at the beginning of this lecture, it's easy to calculate K if you know the equilibrium concentrations of all the reactants and products. In the first few problems we solved, we were given the equilibrium concentrations of all reactants and products. So all we had to do was plug them into the expression for K and the answer fell out. But not in this problem. I'm given an initial concentration of H2S and an equilibrium concentration of S2. And here's the key idea. The mole ratios in the equation, 2 to 2 to 1, along with the fact that you are told how much S2 is present at equilibrium, will allow you to determine how much hydrogen is present at equilibrium and how much H2S is consumed. Here's what I mean. You can't form sulfur without at the same time forming hydrogen. So if you know how much sulfur you produced at equilibrium, the stoichiometry of the equation should allow you to figure out how much hydrogen was produced and also how much H2S had to be consumed to do this. And remember, to calculate K, you need to know the equilibrium concentration of H2S. Now, if these hints aren't enough, you may want to just watch the solution. But I'm going to suggest that you try to work this yourself first to see how well you can do on a problem of this nature. Before I go over this problem, I'd like to make one comment. In many of these problems, it becomes verbally tedious, even a bit confusing at times, to always say molar time and time again. Consequently, I may often substitute the word mole in place of the word molar. It's just kind of understood that this is all occurring in a 1 liter container. I begin with 1 mole of H2S, 1 mole per liter, and they tell me that at equilibrium, the concentration of sulfur is 0.15 molar. I am supposed to calculate the value of K. So once again, let's think backwards. Let's go to the end of the problem and ask ourselves, what do I need to know in order to calculate the numerical value of K? K is going to be calculated from the equilibrium constant expression. The equilibrium concentration of hydrogen squared times the equilibrium concentration of sulfur divided by the equilibrium concentration of H2S squared. If I want to calculate K, I need to find all three equilibrium concentrations. One of them is given. They tell me that the equilibrium concentration of sulfur is 0.15 molar. Well, let's see if I can find the equilibrium concentration of hydrogen. Let's look at the equation for the reaction. Sulfur is formed because H2S decomposes. The reactants turn into the products. The stoichiometry of the reaction, the coefficients, tells me the mole ratios in which the products are produced and the reactants are consumed. This equation tells me that when H2S decomposes, every time 1 mole of sulfur is produced, its coefficient is 1, you must at the same time produce 2 moles of hydrogen. You will always produce twice as many moles of hydrogen as sulfur. So let's see what that means. If you decompose enough H2S to form 0.15 moles of sulfur, 0.15 moles per liter, at the same time, I will be forming twice as much hydrogen, or 0.30 moles of hydrogen. So now I know the equilibrium concentration of hydrogen. It's just going to be twice that of sulfur, 0.30 moles per liter. And don't forget to square that concentration when you plug it into the equilibrium expression. So now I've found two of the equilibrium concentrations. Sulfur is 0.15 molar and hydrogen is 0.30 molar, and that has to be squared. But what's the equilibrium concentration of the H2S? This is the trickiest one to find. I began by putting 1 mole of H2S into the container. But when I got to equilibrium, I didn't have all of this remaining because some of it had to decompose to form the hydrogen and sulfur that were produced. I can't make hydrogen and sulfur from nothing. I have to make it from the H2S. The stoichiometry will tell me how much H2S I have to use up in order to produce the amount of hydrogen and sulfur that I did. There are a few ways to reason this out. I think the easiest is just to recognize that the coefficients of H2S and hydrogen are the same. They're both 2. This means that the number of moles of hydrogen produced and the number of moles of H2S consumed will be the same. You have to decompose 1 mole of H2S for every mole of hydrogen you produce. Since I produced 0.3 of a mole of hydrogen, I must have decomposed 0.3 of a mole of H2S in order to do that. Well, a lot of students at this point will plug in 0.3 for the concentration of H2S. That's a very common and understandable error. But the number that has to be plugged into the equilibrium expression is not the amount that decomposed, but the amount that was left at equilibrium, the equilibrium concentration. So how much H2S is going to be left at equilibrium? Well, I put 1 mole into the container initially, and I just used up 0.3 of a mole, according to my calculations. So I guess when I get to equilibrium, I'm going to have 0.7 of a mole remaining. The equilibrium concentration of H2S will be 0.7 molar. And according to our rules for writing equilibrium constant expressions, that concentration must be squared. Now I'm home free. I've got the equilibrium concentrations of all the reactants and products. Now I just plug them into the expression for K, just like the first problems in this lecture, and I grind out the answer. And depending on how you want to round your numbers, you get a value for K of about 2.8 times 10 to the minus second. That's a big jump in equilibrium thinking. And you notice that solving this kind of problem calls upon knowledge of many different concepts. You have to understand stoichiometry, you have to understand molarity, you have to understand equilibrium. You have to understand a lot of chemistry to do this problem. We're assuming that you've got that good base. I suspect that if all you were doing up to this point in the course was canceling units or trying to solve everything by using proportions or a formula or memorizing each problem as a kind of separate, unrelated thing, you might be hitting a wall here. I mean, the poison fruit might just have arrived on your plate if it hadn't been served up a little earlier. But if you've understood all the concepts, you don't care what kind of problem it is. All of them involve the same concepts, just recycled a bit differently. Let's try one more along the same lines. Consider the equation shown on the screen. 2 moles of A and 3 moles of B are placed in a 1-liter container. Notice that I have purposely used moles of A and B that are not related to their coefficients in the equation. A and B are allowed to establish equilibrium. At equilibrium, the concentration of C is equal to 0.60 molar. calculate the numerical value of K. If you solve this problem correctly, you can be very proud of yourself. I mean, there is a lot going on in this problem. If I'm going to calculate the numerical value of K, I need to calculate the value of the equilibrium constant expression, the concentration of C cubed times the concentration of D divided by the product of the concentration of A times the concentration of B squared. And all four of these concentrations must be equilibrium concentrations. You know, we call this an equilibrium problem. I mean, and it is. But the last step, the thing that actually has to do with equilibrium, is really the easiest part of the problem. This is really more of a stoichiometry problem. Can I successfully use the coefficients in the equation to find the equilibrium concentrations of all the reactants and products? Here's how you can do that. The initial concentration of A was 2 molar, and the initial concentration of B was 3 molar. Then they tell me that when I get to equilibrium, the concentration of C is measured and found to be 0.6 molar. I know this number. The equilibrium concentration of C is 0.6 molar, and that has to be cubed. So what would be the equilibrium concentration of D? Well, the coefficients in the equation tell me that for every 3 moles of C you produce, you only produce 1 mole of D. You only produce 1/3 as much D as C. And now I'm going to take a small jump and stop writing out this relatively easy calculation in the former somewhat laborious manner. We're just going to think this through logically and write things down more simply. But if your teacher demands that you continue to write things in the more technically correct manner, then please do so. And this is preferred by many teachers and may very well be the better thing to do. But we'll take a notational shortcut if you don't mind. So when 0.6 moles per liter of C are produced, only 1/3 as much, or 0.2 moles per liter of D are produced. So the concentration of substance D at equilibrium is going to turn out to be 1/3 the concentration of substance C at equilibrium, 0.2 molar. And that only has to be taken to the first power. Now I have found the concentrations of both products at equilibrium. What are the concentrations of the reactants? That's always a little trickier to calculate because to find the concentration of the reactants, you have to do 2 things. You must take the amount of each reactant you put into the container initially, what you started with, and then figure out how much was consumed as the system approached equilibrium. Subtracting the amount consumed from the amount you started with will then tell you how much remains at equilibrium. It's sort of like if you started with $50 and you went shopping and spent $30, you would have $20 remaining. So let's see what that would be. Again, we have to look at the equilibrium, at the coefficients. For every 3 moles of C that are produced, 1 mole of A is consumed. So I only consume 1/3 as much A as I produce of C. I started with 2 moles per liter of A. I produced 0.6 of a mole per liter of C, which means that I consume 1/3 of that, or 0.2 moles per liter of A, as I approach equilibrium. This means that when I finally reach equilibrium, the amount of A remaining will be 2 moles per liter that I started with, minus the 0.2 of a mole per liter that was consumed, or 1.8 moles per liter of A remaining. What about B? Similar reasoning. I start with 3 moles per liter of B. Here the stoichiometry is a little more tricky. I use up 2 moles of B for every 3 moles of C produced. So if I produce 0.6 of a mole per liter of C, I will consume 2/3 that much, which turns out to be 0.4 of a mole per liter of B. Starting with 3 moles per liter and consuming 0.4 of a mole per liter will leave me with 2.6 moles per liter of B remaining at equilibrium. I have now found the equilibrium concentration of A and the equilibrium concentration of B. B must be squared. We evaluate this expression, and the value for K turns out to be about 3.6 times 10 to the minus third. All of the problems we have solved today involve general types of reactions. In the next lecture, we're going to take a look at a very specific and special equilibrium, the self-ionization of water.